All right, let's dive right into this explainer and explore the invisible infrastructure that keeps massive applications running smoothly long after the initial code is written. Today, we're looking at the critical non-functional requirements that really separate a small weekend hobby project from a global, data-intensive powerhouse. We so often get caught up in exactly what an application does, but today, we're focusing entirely on how well it does it when put under extreme pressure. Here's our architectural blueprint for today. We'll quickly move through Section 1, the social network challenge, followed by measuring system performance, reliability, and fault tolerance, achieving system scalability, and wrap it all up with designing for maintainability. Okay, Section 1, the social network challenge, and the very real stakes of scale. To really set the stakes here, I want you to imagine a system that has to handle 500 million daily posts. Think of a platform like X, formerly Twitter. That averages out to about 5,800 posts per second. But wait, it has peak spikes of up to 150,000 posts every single second. If we just used a standard relational database and tried to dynamically query the timeline for every single user on the fly, finding who they follow, merging all the recent posts, we'd be looking at over 400 million database lookups every second. So the reality is, reading a timeline dynamically on the fly would absolutely crush the database. Your users would just be left staring at a spinning wheel of doom. So how do engineers actually solve this? Well, they use a really clever process called fan-out. Instead of querying everything on the fly the moment a user opens the app, the system pre-computes the timelines. It's honestly exactly like delivering a single physical letter to millions of individual mailboxes. When a user posts a post, the system actively pushes that new post into a cached timeline for every single person following them. Think about how a single post from a user cascades perfectly into the pre-computed timeline caches of all their followers. Now, when a follower logs in, the system just hands them their ready-made timeline. It is incredibly fast for reading. Though, as you can imagine, it does mean the system has to do a massive amount of heavy lifting behind the scenes whenever someone writes a post. Moving on to Section 2, measuring system performance, and why we have to look way beyond the average. People mix up latency and response time all the time, but we really need to be precise here. Latency is just the duration a request is sitting around waiting to be handled. But response time, that's what the client actually experiences. It includes the processing time, plus all those messy, unpredictable delays in the network and the queues. It is the true measure of your user's experience. Here is the thing. Averages flat out lie to you. They get completely skewed by extreme outliers, so we have to rely on percentiles. The median, or P50, tells us what a typical half of our users experience, but to see how bad things actually get, we have to look at the 95th and 99th percentiles. The P99 represents the absolute worst 1% of requests. And interestingly enough, massive companies like Amazon care deeply about the 99.9th percentile. Why? Because the customers experiencing the slowest requests are often the ones with the most data on their accounts, meaning they're frequently the most valuable users. When you map this out, you can clearly see these tail latencies sticking out like massive spikes above the median and even the 96th percentile lines. If we only looked at the mean or average, we would completely hide the fact that some of our users are experiencing terribly slow load times. And how does this turn into a massive headache? Well, a single user request often requires multiple back-end database calls just to assemble a single page. It literally only takes one slow back-end call to hold up the entire process. We call this tail latency amplification. Even if only a tiny fraction of back-end calls are slow, as your system grows more complex, the chances of hitting one of those slow calls skyrockets, which can ruin the whole experience for the end user. All right, Section 3, reliability and fault tolerance, or as I like to call it, surviving reality. Let's compare what can actually go wrong. Hardware faults, like a hard drive randomly crashing or a power supply failing, are usually pretty independent. We fix them simply by throwing redundancy at the problem. RAID arrays, backup generators, multiple servers. Software faults, on the other hand, they are far more dangerous because they are highly correlated. A bug in a shared module can cause every single node in your system to crash simultaneously. Fixing those requires deep system design, strict process isolation, and just constant monitoring. At the end of the day, reliability simply means your app continues to work correctly, even when things around it are failing. We build fault tolerance into systems so that a localized fault, say a single server dying, doesn't trigger a catastrophic meltdown of the entire application. In a distributed system, you just have to assume things will fail constantly. You design the software to gracefully handle those partial failures behind the scenes so the user never even notices. Section 4, Achieving System Scalability. Let's talk about coping with explosive growth. So let's say your system is lightning fast and perfectly reliable today. What happens when you go viral and gain 10 million users overnight? When your throughput hits the absolute limits of your hardware, things get ugly fast. Response times don't just slow down gradually, they skyrocket exponentially. This is entirely due to queuing delays. Your CPU is busy crunching earlier requests, so the new incoming requests just sit in a queue waiting, driving up the wait time for the user until the system eventually just buckles. To keep that response time from exploding, we need real scalability strategies. First off, you have to measure your exact load. Are you read-heavy or write-heavy? Because honestly, there is absolutely no generic magic scaling sauce. An architecture built for a few massive data dumps is totally different from one handling millions of tiny text posts. Often, the goal is to use a shared nothing architecture, strategically breaking the system down, which is a process called sharding, so you can easily distribute all that massive load across hundreds of smaller, independent machines. Finally, Section 5, Designing for Maintainability. This is playing the long game. It is an open secret in software engineering that the vast majority of your cost isn't the initial coding, it's the ongoing maintenance. A genuinely maintainable system has to nail 3 areas. First, operability. You need to keep your ops team sane with good monitoring tools. Second, simplicity. Keeping the codebase clean so new engineers don't accidentally break things on day one. And third, evolvability. Building an agile architecture that can adapt to whatever crazy, unpredictable requirements the business throws at you next year. If we fail at that second one, simplicity, your project evolves into what developers literally call a big ball of mud. The absolute best tool we have to guarantee simplicity is clean abstractions. A good abstraction just hides all those messy, complicated implementation details behind an easy-to-understand facade. It lets different parts of your system talk to each other without needing to know exactly how the other side is wired. I'm going to leave you with this provocative thought to really challenge how you view system design. Code doesn't rust, right? It doesn't suffer from material fatigue. So why on earth do we spend so much time and money maintaining it? Well, it's because the environment, the sheer scale of the user base, and the business requirements never, ever stop changing. Building a great system isn't just about making it work for today. It's about engineering a flexible foundation that can actually survive the unknown demands of tomorrow.